Hi, online student. Can you hear me? Excuse me. Can you hear me, online student?
Yes,
Hello. Can you hear me?
yes, we can hear you.
Yeah, thank you. Okay, so we will start at 4:05 or 4:02 because some student is coming here. Okay. So as I said yesterday in my lecturer class, the tutorial question you can find in learning materials. Yeah, this one, learning materials and tutorials. Okay. So in here you have question and solution of 11 tutorials. 11 tutorials from week 1 to week 11. And each week you will have from 3 to 4 questions. However, we only do maybe 2 or 3 questions in the class. Okay, you will have 1 or 2 questions you have to try to do by yourself. Okay, and actually the solution is you can see the solution already. For example, with tutorial 1 here. Okay, we have the solution. Okay, so if you have any question, you can email me. I will give you the more detailed solution. Yeah, and I suggest I highly recommend that you read this one, read the question and solution before you come into tutorial class. Okay, so it's easier for you to understand and give you any question. Yeah, and because yesterday we have a short lecture because we use 45, 50 minutes to introduce about the subject, about the material. Okay, so yesterday we haven't finished thermodynamics, fluid mechanics properties, not finished. We only study about some properties like density, vapor pressure, and left thread or something like that. Okay. So today we only do some question in the tutorial 1. Okay. Just only some question, not all. For example, here, this one tutorial 1. Okay. We have 1, 2, 3 questions. Which question 1 is some example of fluid and example of application of fluid mechanics. This one I said yesterday. Okay. We have so many applications of fluid mechanics. Like as I said, if you want to pump water from the ground level to the higher level, you have to buy a pump. And how to buy a pump? You have to know the pump power. Okay. And fluid mechanics will have you find pump power. Or for example, we have a aircraft. How to lift the aircraft to the higher level? We have because when the aircraft moving, we have 2 forces applied to aircraft. It's drag force and lift force. Lift force will lift the aircraft to the higher level. Okay, so fluid mechanics will help you find the drag force and lift force. Or inside the body, you have a pump. It's a heart. Okay, the heart will pump blood to whole body. without the Zohars, you die. Okay, and in this case, we have to use the blood pump. Blood pump is a project. You have looked in the subject outline. I said yesterday we have you have a project. This one project, okay, and project is about blood pump. Project will be submitted on week 9, and this one is a group project. Yeah. So we have so many applications of fluid mechanics. Okay, so this one is question 1 application. You can try to find some application of fluid mechanics for yourself. Okay, we will start from question 2. Question 2 will have you more understand about fluid mechanics properties and how to find properties using the table or figure. Okay. Question 2 in the tutorial 1. Let me see. We'll say use question 2 in tutorial 1. Oh no. Let me see what's problem. What's the problem with this one? Okay. It's stuck here. It's frozen. Reconnect again. Sorry, something wrong. Okay, can you see it? This on question 2. Excuse me, online student, can you see my iPad? Question 2.
Yeah, okay.
Okay, so you see this on question 2. Because yesterday we only studied about the density, the vapor pressure, and temperature and pressure and density and boiling temperature and lab rate. So today we only work together in some question like question 1, 2, 3. Surface tension of water we will study next week. Bulk modulus next week. Kinetic viscosity next week. This one. Gas constant are pressure and temperature and density in the US standard atmosphere and the lab rate. Okay. Boiling temperature. Okay. We only have 1, 2, 3, 4, 5, 6, 7 questions, small questions. And after that, I will give you some let's see, multiple choice question. It's similar to the quiz, okay? And you have to practice on the multiple choice question, okay? So we will start with the question 1. You have to find the density of air in standard condition, water and seawater at 20 Celsius, mercury at 20 Celsius. Density. How to find density? density. I will open. Let me see. This one, okay. Okay, we have to find density, and this one is the cost node. Okay, as I said yesterday, in fluid mechanics we have textbook. Textbook is fluid mechanics, Mosul 7 edition, SIS. Okay, and if you can't buy a textbook or can't borrow a textbook from UPS library, you can use the course note. The course note you can download on UPS Online. It's free. Okay, it's free. So in the course note, at the end of this course note, in the appendix, you can see some table. This one is appendix. Appendix. Yeah, appendix. Okay. Appendix, and in the first question, it asks you find the density of air in standard condition. Water and seawater at 20 Celsius, mercury at 20 Celsius. Okay. Standard condition, use table. For example, here you have approximate physical properties of some common gases at standard atmospheric pressure, SI units. Okay. Standard atmospheric pressure is 101.3 kPa at sea level. Pressure at sea level. We are living in 101.3 kPa. Yeah. And the density, you have air density is 1.23 kilogram meter cube. Okay. Just only use the table, you can find the result. The first week we study about fluid mechanical properties, and you to find properties, you know where to find properties, with where to find table. Okay, in the course note. Okay. First one here. Okay, density of air in standard condition. Use table 2. Okay. And density of air in standard condition is 1.23 kilogram per meter cube from the table in the appendix. Okay. And density in standard condition. Remember that this one is in standard condition because for air we have adiabatic equation. Density depends on pressure and temperature. Okay. So for example, because in the standard condition, the pressure is 101.3 kPa and temperature is 15 Celsius, we have the density is 1.23. Okay. But if pressure is 101.3 kPa, but temperature increase to 100 Celsius, the density will be different because density depends on adiabatic equation, depends on pressure and depends on temperature. Because we have to remember the adiabatic equation. Adiabatic equation, pressure equal to rho R T. Okay, so the density equal to pressure divided by R times T, which R is a gas constant. R is gas constant. R you can find it from the same table. Okay, P pressure and T is the temperature. And SI unit of pressure is Pascal. SI unit of temperature is Kelvin. Okay. Gas constant from this table. This one. Yeah, this one is gas constant. R. For example, for air, R is 287. Okay. 2.869. E plus 2, which means 286.9 joule per kilogram Kelvin. Okay. Or 287. So density depends on pressure and temperature. So the density in the question 1 is 1.23 kilogram meter cube, just only in standard condition. Standard condition mean pressure is 101.3 kPa and temperature, 15 Celsius only. Okay. Question 1. The second one, you find the density of water, seawater at 20 Celsius, mercury at 20 Celsius. Okay. Air is gas, but water, seawater, and mercury is liquid state, and it's incompressible substance. Incompressible substance, it means the density is almost constant. Okay, the density of liquid almost constant. You can double check in okay. The table in the course note. Okay, the table in the appendix of the course note. This one, the course note. You can download on UTS Online. Okay. Yeah, for example, for physical properties of water, okay, you see the density. Density at 0 Celsius is 999.8. 5 is 1000, 999.7, 999.1, almost constant. So for water, in fluid mechanics, when you see water, you can use density of water is 1000. Okay, don't worry about 999.1, 999.7, 1000 water. Okay, because water is incompressible substance. Incompressible substance, so density is almost constant. Okay, so the density of water 1000. Density of seawater. Okay, seawater. For seawater, you use table 1. You have approximate physical properties of some common liquids. Yeah, liquid. Seawater at 15.6 Celsius is 1030 kilogram meter cube. So as I said, seawater is liquid. Liquid is incompressible. So the density of seawater is constant. So at 15.6 or 20 or 50, 1030 kilogram meter cube. Okay, 1030 kilogram meter cube. It's a little bit higher than water density of seawater. And mercury at 20 Celsius is 13,600. Yeah. 13600 kilogram meter cube. Density. Okay. Density of liquid of gas you have from the table. Okay. For gas, density based on pressure and temperature. For liquid, constant. Okay. So you will have density of water is 1000 kilogram meter cube. Is the course note available on UTS Online? Yep. Course note. Thank you. Thank Maria. Okay. Water is 1000 constant. Okay. Seawater 1030 kilogram meter cube constant, and density of mercury 13600 kilogram meter cube. All of them from table. Okay, in the appendix. Okay, so for liquid, you have density, so density is constant. Okay, for gas, density depends on pressure and temperature. pressure, temperature based on ideal equation. Okay. The first question. Got it? Do you have any question? Do you have any question? No? Question 1, okay. Question 2, vapor pressure of water. Yeah, this one. Vapor pressure of water as 5, 20, 50, 100 Celsius. Vapor pressure. We have to find vapor pressure, it means PV, at 5, 20, 50, and 100 Celsius. What is vapor pressure? What we discussed yesterday, vapor pressure. What is vapor pressure? Yesterday, I gave you one example. At the sea level, you have water boil at 100 Celsius. Okay, sea level. Oh, what's it? So I can see. Yep, the pressure at quick water boils. Yep, it's correct. When we go to the high mountain, the pressure, this one is PO, this one is TO. Pressure PZ, SZ. PZ will be smaller than PO. And at this pressure, the water boil at PZ smaller than TO. Okay. For example, we go to the high mountain, and at the high mountain pressure is around 70 kPa. Water boil only 90 Celsius. Okay, 90 Celsius. And in this question, it's asked you for PV at 5, 20, 50, and 100 Celsius. So PV at 5, PV at 20 Celsius, PV at 50 Celsius, and PV at 100 Celsius. Okay, and where to find this one? From the table in the appendix again. This one, this table, physical properties of water. Okay. So with the vapor pressure, we depend on temperature. Okay. Vapor pressure depends on temperature, and boiling temperature depends on pressure. Okay. If you study thermodynamics, this state we call is saturated. Saturated. If we have a saturated substance, it means pressure and temperature is dependent properties. It means when we have pressure, we can find temperature. From temperature, we can find pressure based on this table. Yeah. For example, here, at sea level is 101.3 kPa. Water boil at 100 Celsius. Okay. It means if we want to have water boil at 100 Celsius, we have to create the pressure is 101.3. Okay. And similar, if we want to make the water boil at only 5 Celsius, we have to create a pressure just only 0.87. Okay. For example, we have a container, and the pressure, water pressure inside the container is 0.87 kPa. Water boil is only 5 Celsius. 0.87. Okay. So water boil is just only 5 Celsius. Okay. So in here we have at 5 Celsius, we have vapor pressure is 0.87 kPa. Unit is kPa. Okay. At 20 Celsius, if we want to make water boil at 20 Celsius, we have to create a pressure at 2.34 kilopascal. 2.34 kPa. Okay, and at 50 Celsius, we have here 50 is 12.33 kPa, and 100 Celsius is standard condition 101.3 kPa, or sea level. Standard condition as sea level. Okay. So vapor pressure is here. The friend mentioned about vapor pressure. Oh, what's that? Vapor pressure is the pressure at which water boil. Okay. Vapor pressure is pressure at which water boil. And it's similar to this question. We have the question about boiling temperature. Boiling temperature of water at 8,000 meter altitudes. Okay. If you have a look at the table, this table, okay. If we have temperature, we can find vapor pressure is the last column, okay. And if we have pressure, we can find the first column will be is boiling temperature, okay. It means if we have the pressure is 101.3, water boil at 1,000. If we have pressure is 19.92, water boil at 60. Okay, so in this question is this question. This one is the question, the last question in question 2. Boiling temperature of water at 8,000 meter altitude. Okay, we move to the last one because boiling temperature and vapor pressure is very similar. Boiling temperature of water at 8,000 meter altitudes. How to find the boiling temperature? What we have to find the boiling temperature? To find boiling temperature, it means you can find boiling temperature if we know pressure, because from the pressure based on the table we can find boiling temperature. But how to find pressure at 8,000 meter altitudes? You have to find boiling temperature TB at 8,000 meter. Boiling temperature TB at 8,000 temperature. And we have to find this one, TB. It means we have to know pressure at 8,000 meter altitude. Okay, if we know pressure, based on the table, you can find boiling temperature. And how to find pressure at 8,000 meter altitudes? We base on the table, this one, table 4. The US standard atmosphere, SI units, okay, 8,000 meter altitudes, it means 8 kilometer. And at 8 kilometer, the pressure is 35.65 kPa. Okay. When we go up, pressure decrease. At 8 kilometer, the pressure is only 35.65 kPa. Okay. 35.65. So we have pressure at 8,000 meter altitude is 35.65 kPa. This one from the table in the appendix. 8,000 meter altitudes. Okay, so now from the pressure, you can find temperature based on the previous table, this one. The last one is pressure. The first one will be is boiling temperature. Okay, boiling temperature. But the pressure here, you see our pressure is 35.65 kPa. But in this table, we only have 31.16, 47.34, 70.10. We don't have 35.65 kPa. How to find temperature based on this table? How to find? Okay. For example, at 31.16 kPa, we have temperature is 70. At 47.34, we have temperature is 80. But we don't have 35.65. How to find temperature? Interpolate. You remember it? Interpolate. It means this one. For example, from the table, you have this one as temperature is 70. You have pressure here is 31.16. Okay, from the table. At 80 Celsius, we have pressure is 47.34. Okay, this one is Celsius, kPa, kPa. This one from the table, yeah, this one. 70, 31.16, 80, 47.34, okay? And the pressure is 35.65 between 31.16 and 47.34. And you have to find temperature T. So interpolation equation. So you have T minus 7T over 8T minus 7T, T minus 7T divided by 8T minus 7T will be equal to 35.65 minus 31.16 divided by 47.34 minus 31.16. Interpolation equation. Okay. T minus 7T equal to over 8T minus 7T equal to, in the right hand side we have pressure 35.65 minus 31.16 divided by 47.34 minus 31.16. So from here you can find temperature. And the temperature existing here is around, let me see the result, between 70 and 80 here we have 72.8 Celsius interpolation. This one you have to use so many times in fluid mechanics. Okay, because in the table we don't have all value in the table. We only have the main value. Okay. For example, at 70 and 80, but we don't have 71, 72, 73. Okay, so to find a 71, 72, 73 interpolation. Okay. So the boiling temperature at 8,000 meter altitude is 72.8 Celsius. This means when we go up to 8,000 meter, water boil at 72.8 Celsius only. Okay, 8,000 meter altitude, water boil at 72.8 Celsius. Got it? Do you have any question about vapor pressure and boiling temperature? Do you have any question? No? Okay. So we finish this one, and boiling temperature. Viscosity next week, not this week. Viscosity and kinematic viscosity next week. Because this week, yesterday is a short lecture. We only mentioned about vapor pressure, density, and lap stress, also that's boiling temperature. Okay, not viscosity or elasticity next week. Engineering gas constant R for air standard condition. I mentioned about R already in the question 1. Okay, R is a gas constant, and this one is constant for one kind of gas. For example, it's constant for air. It's constant for mercury. It's constant for argon, not mercury. Not mercury is a liquid, not gas. Okay, and here you have some common gases. Okay, gas constant R is constant for air in all conditions. It's constant in the standard condition. It's constant at 8,000 meter altitude. It's constant at more than 8,000 meter altitude. Its always is 287 or 286.9 joule per kilogram Kelvin for air. Okay, and for carbon dioxide, you see you have the different values of R. Here is 188.9. For helium is 207.7. 2077. Be careful, okay, because E plus 2, but for helium E plus 3. Okay, E plus 3 it means this one will be 2077 joule per kilogram Kelvin. So be careful. Okay, gas constant. So gas constant you have from ideal gas equation. You use in ideal gas equation. Okay, and you got this one in question 1. I mentioned about the ideal gas equation in question 1 already. Constant, and from the table. Gas constant from the table. For air is 287 joule per kilogram Kelvin. Do you have any question? No? All right, students, do you have any question? No? So next question, you have to find pressure, temperature, and density of ambient air in US standard atmosphere at sea level. Altitude is 1,000, 2,000, 5,000, 10,000. Check ideal gas equation, P equal to RT for all these cases. You find pressure, temperature, and density. Okay. You find pressure, temperature, and density at sea level, 1,000 meter, 2,000 meter, 5,000 meter, and 10,000 meter. Okay. Pressure, temperature, and density at sea level, 1,000, 2,000, 5,000, and 10,000. Okay, this one is air. So use table, you know. US standards atmosphere. sea level is mean 0. Okay. And we have temperature, pressure, and density. At 2,000, at 10,000 is that's okay. But how to find temperature, pressure, and density at 1,000 and 5,000? Okay. Sea level, 2,000 and 10,000 we have from on the table already. For example, sea level we have temperature is 15, pressure is 101.3, and density is 1.225 kilogram meter cube. Okay, but how about pressure, temperature, and density at 1,000 meter altitude? 1,000. We don't have from the table. How about the properties of air properties at 1,000? How about 1,000? Okay. At 0 or sea level, 2,000 or 2 kilometer, 10,000 or 10 kilometer from the table. But at 1,000 meter, 5,000 meter, we don't have from the table. How to find properties, air properties at 1,000 and 5,000? Interpolation, yeah. Because we have the properties at 0 and 2. Okay, so we can find the properties at 1 kilometer. Okay, at 1 kilometer. For example, we find at 1 kilometer or 1,000 meter altitudes. We have the altitude is 0 kilometer, sonic temperature, sonic pressure, and density. Okay, at 2 kilometer, at 0, we have here is 15 Celsius, pressure is 101.3, and density is 1.225 kilogram meter cube, KPI. Okay, at 2 kilometer, let me see. The temperature is 2 Celsius. Pressure is 79.5 kPa. And density is 1.007 kilogram meter cube. Okay. Yeah, this one we have from the table. From the table, we have this one. Okay. And we have to find the properties, air properties at 1,000 meter or 1 kilometer. We have this one is T1, this one is P1, and rho 1. Okay. So interpolation, we will have similar to previous question. We have 1 minus 0 divided by 2 minus 0 equal to, for the temperature, T1 minus 15 divided by 2 minus 15. Okay, equal to pressure, P1 minus 101.3 divided by 79.5 minus 101.3, so 1. Okay, equal to density, rho 1 minus 1.225 divided by 1.007 minus 1.225. So you can find temperature, pressure, and density at 1 kilometer. Interpolation. Okay, so that's why I said interpolation equation you have to use so many times in fluid mechanics. It's similar for 5,000 meter altitudes. Okay, similar for 5,000. For 5,000, you use at 6 km and 8 km. Yeah. So from here you can find temperature, pressure, and density at 1 km altitude. Got it? Do you have any question? So similar, you can find at 5,000 meter altitude. Okay, do you have any question? Any question? Also. Okay. So this one. And you can check the Adiabatic equation, P with rho RT. Okay, P with rho RT. From the table, you can find temperature, you know pressure, and you know density. And R is constant. R for air is 287 joule per kilogram Kelvin. Okay. So based on the data you have from the table, you can double check the Adiabatic equation, P equal to rho R T. Double check, and so that's one is correct. Okay. And so that is one is correct. You can double check. P, remember that P you have to convert to Pascal, not kilopascal. Okay. Temperature, not Celsius, can be scale. Okay. For example, at zero sea level, okay, pressure will be is 101,300 Pascal. Density 1.225 kilogram per meter cube SI unit. Okay, R 287 joule per kilogram Kelvin, and temperature 15 Celsius plus 273 or 288 Kelvin. Okay, the units is very important. Okay, unit pressure is Pascal, not kilopascal. Unit of temperature is Kelvin scale, not Celsius. Okay, so you can apply it to the Adiabatic equation. So that is correct. Okay, similar, you can double check at 1 kilometer, 2 kilometer, 5 kilometer, and 10 kilometer. Yeah, this one is sea level or 0 kilometer. Okay, you got it? Do you have any question? Yep. That's constant. 27. The unit is joule per kilogram. This unit of joule per kilogram. All of them is SI. Joule is SI unit of kilogram is SI unit of mass, and Kelvin is SI unit of temperature. Joule per kilogram Kelvin. So unit in fluid mechanics is very important. So that's why I said before any calculation, you have to convert to SI unit. Okay. And SI unit. Here, I think we have here. Okay. Units. Pressure is Pascal. Temperature is Kelvin. Mass is kilogram. Of some main properties only: Kelvin, kilogram, pressure, force, is Joule. Okay. The SI unit. Yep. Joule. So sorry, no, not force. Sorry, it's energy. Is Joule. Sorry. Force is Newton. Sorry, it's energy. Force is Newton. Sorry. Energy. Okay. Do you have any question? The last one in the question 2 we will do today, we work together today, is a lap thread B. Okay, lap thread B. This one I mentioned about this one in the lecture class yesterday. The lap thread B in US standard atmosphere below 10,000 meters of altitude. Okay, and lap thread B equal to change in temperature divided by corresponding change in altitude. This one, actually we did this one yesterday already. We have lap thread B equal to change in temperature dt over dz in altitude. dt over dz. For example, here from this table, okay, at the altitude 0 kilometer, we have the temperature is 15. At 2 kilometer, we have the temperature is 2. So change in temperature is 2 minus 15 will be is, for example, at between 0 and 2 kilometer, 2 minus 2 minus 15. Change in altitude is 2 minus 0, and this one will be is minus 6.5 Celsius per kilometer. The unit is Celsius per kilometer. This means when we go up 1 kilometer, the temperature will decrease 6.5 Celsius. 6.5. We go up 1 kilometer, the temperature decrease 6.5. And you see from 0 to 10 kilometer, okay, from 0 to 2, change 30. So 1 kilometer is 6.5. From 2 to 6, 6.5. 6 to 8, almost 6.5. From 8 to 10, almost 6.5. This one is lap thread. It means when the altitude increase from 0 to 10 kilometer, the lap thread is 6.5 Celsius per kilometer. But higher than 10 kilometer is incorrect. Okay, we don't have the lap thread. The lap thread is 6.5 only for the altitude from 0 to 10 kilometer. Okay, because you see from 10 to 12, the temperature decreased from minus 49.9 to minus 56.5. It's smaller than 6.5. Or from 12 to 14, almost constant. 16, almost constant. 18, almost constant compared with 12. So the lap thread, we only use lap thread for the altitude from 0 to 10. Okay, only. And the lap thread, as I mentioned in the lecture yesterday, lap thread, let's see. Yeah. Okay, the lap thread. This one. Okay, lap thread is delta T over delta Z is 6.5 in standard condition, and it's correct for the altitude from 0 to 10. But if we don't have standard condition, we have dry adiabatic lapse rate will be 10 Celsius per cubic meter. Dry adiabatic is mean dry air, and adiabatic is mean no heat transfer. We will have the lapse rate is 10 centimeter per kilometer. 10 Celsius per kilometer. Okay, in dry adiabatic lapse rate condition. For isothermal atmosphere is mean the temperature is constant. Isothermal. When temperature is constant, it means the lapse rate is 0. Okay, so it depends on the condition, standard condition or dry adiabatic condition or isothermal condition. We have a different lapse rate. Okay, lapse rate 6.5 only for standard condition. Dry adiabatic 10, isothermal 0. Okay. Got it? So do you have any question before we come into a small multiple choice question? I will give you a few minutes to finish my question today. Okay, because the quiz, as I said, online, open book, and MCQ, multiple choice. Okay, so that's why I prepare a multiple choice question for you to have you more familiar with my style, lesson style. Okay. Here, this one is my question today. What's wrong? Disconnect. Do you have any question before we coming to the multiple choice question today? This question is not in the tutorial question. Okay, it's additional question because yesterday we have a short lecture. Okay, this one is my question today. We have the pressure gauge pressure of a container containing air with minus 20 kPa. We have a container and we have a pressure sensor. And for the pressure sensor, gauge pressure sensor, we have we read is minus 20 kPa. It's so minus 20 kPa. And the container is at location 4 kilometers above the sea level. The absolute pressure of air inside the container is A, B, C, and D. Okay. So for this one, we have a container. This one is sea level. This one is sea level. Okay, but we have a container at 4 kilometer altitude. And in this container, we have a pressure sensor. And from this pressure sensor, we rate is minus 20 kPa. And we have two questions. Question one, ask you the pressure inside the container, P. Pressure inside container. Okay. And the second one, okay, we do the first one first. We give you maybe 5 minutes to do the first question. The question I. We have the pressure gauge of a container containing air is minus 20 kPa. and the container is at the location 4 kilometers above sea level. You have to find the absolute pressure of the air inside the container. And we have 4 answers. Which one is correct? Which one is correct? You have to find absolute pressure, P absolute, inside the container. The container is located at 4 kilometers above the sea level. And from the pressure sensor, we have rate pressure sensor is minus 20 kPa. Which one is correct? First one 82 kPa. Second one is 62 kPa. 42 kPa or 22 kPa. Which one is correct? Okay. So you have 5 minutes and give me the answer A, B, C, or D. A, B, C, or D. C. Okay. We have 1C. Anyone have the different answer? C. 42 kPa. Please show me the answer, online students. C. We have 1C. Anyone have the different answer? A 82, B 62, C 42, and D 22. Which one is correct? Sorry, where's my son? Okay. So for question 1, the correct answer is C, is correct. Yeah, why you have C? Yeah. Yeah. Yep. So you have ambient pressure. Yep. Yeah, it's correct. because we have to find absolute pressure. And absolute pressure of air inside the container will be equal to gauge pressure plus ambient pressure. Okay, this one is ambient pressure, but ambient pressure at 4 kilometer altitude, not at sea level, because the container is located at 4 kilometer altitude. Okay, so absolute pressure equal to gauge pressure plus ambient pressure at 4 kilometer altitude. The equation we have yesterday. Okay. C. Yeah, the answer is C. Is what? Here, this one. Okay. Absolute pressure equal to ambient pressure and gauge pressure. Okay. And gauge pressure is mentioned in the question is minus 20 kPa. Okay. Ambient pressure at 4 kilometer altitude. You have from the table 4 kilometer is 61.64. Okay, 61.64. 61.64 kilopascal. Okay, so the you have absolute pressure will be 41.64 kilopascal. And just have a look in the answer 82, 62, 42, and 22. So closest with our answer is 42. So you choose C, 42. Okay, because in the fluid mechanics, the difference is smaller than 5% is very good. So 41.64 or 42, very good. Okay. But 22, no, 50%. The difference is 50%. 62, maybe 25%. 82, 50%. So the answer closest with our answer is 42. Or that we choose C in the answer sheet. Okay. So this one will be similar to the quiz. Okay. If the answer, if you find 41.64 and you double check in the answer sheet, closest answer. Okay, closest answer. You don't have exactly 41.64 in the answer sheet. Yeah. The table. For 61. Yeah. Absolute pressure. This one is ambient pressure. It's the absolute pressure of ambient. Okay, this one is ambient. You see, you have standard atmosphere. This one is pressure of atmosphere. Okay. The absolute pressure of the ambient. Yeah, of the ambient. And in this question, we find absolute pressure of air inside the container. Okay. Okay, so question 1, the answer is C. Question 2, Question 2. If the air inside the container is at the same temperature as the ambient air in the standard atmosphere, and the volume of the container is 2 meter cube, the container air mass is 4 options. Okay. For question 2, we have the temperature in the container, the temperature inside, temperature T, is same the temperature at the as ambient air in the standard atmosphere, in the standard. Okay, the temperature inside this container is the same with air as the standard atmosphere. And the volume of the container V 2 meter cube. Okay. And you have to find mass. How many kilogram air inside the container? Okay. Question 2. You know the temperature, air temperature inside equal to air temperature standard condition. And you know the volume of the container is 2 meter cube. You find the container. You have a mass of air inside the container. Five minutes. You have 4 options. 2.06, 1.72, 1.11, and 0.76. And which one is correct? This one is correct. Which one is the answer? Which one is the answer? A, B, C, D. How many kilogram? Oh my God! Some what's problem? Sorry, something wrong. Okay. A, B, C, or D? A, B, C, or D? All right, student. Anyone have the answer? A, B, C, or D? How to find mass? You have to find mass. How to find mass? Yeah. So mass, you can find if you know density and volume. The volume you have is 2 meter cube already, the volume. Okay, because mass, because you have mass equal to density times volume. How to find the density? Air density inside the container. Not air density at 4 kilometer altitude. Air density inside the container. Inside and outside different. Outside is atmospheric pressure, but inside now. And how about density? Air density inside the container. How to find density? You can find density if you know. You see here, what I said here. What's this one? Yeah. Density, liquid is constant, but gas density depends on pressure and temperature and ideal equation. Okay. It means you can find density if you know pressure and temperature inside the container. Based on ideal equation. Ideal equation is mean P equal to rho RT. So rho equal to P divided by RT. Okay. And pressure you have in the question 1. Yeah, pressure, absolute pressure inside the container, question 1. And temperature equal to temperature a standard condition. It's mentioned. Okay. This one is a process to have the mass from density and volume. Volume, you got it? So density from ideal equation based on pressure and temperature. Pressure, you got it in the question 1. Temperature equal to temperature as standard condition. Yeah, the temperature at the same temperature as the ambient air in the standard atmosphere. Standard atmosphere. Okay. So I give you maybe 2 or 3 minutes to give me the answer here. Okay. Pressure in question 1, it means pressure is 41640 Pascal, or you can use 42,000 Pascal. It's okay. Okay, pressure is question 1. Yes, R is 287. R is gas constant. It's constant. And R is 287. Yeah. Temperature. The same temperature as the ambient air in the standard atmosphere. But in this case, everything is located at 4 kilometer altitude. Okay, so air at standard condition and 4 kilometer altitude, not sea level. Okay, because this container is at 4 kilometer altitude. So at 4 kilometer altitude here, we have the temperature. So you see, standard atmosphere at 4 kilometer altitude is minus 11 Celsius. Okay, so this one is minus 11 Celsius, or equal to minus 11 plus 273, or this one is 263 Kelvin. Okay, 263 Kelvin. Standard, but at 4 kilometer altitude, not standard.
That's
Yep.
262.
Yeah, 262. So thank you. 262. Yeah. 262 Kelvin. Okay. So and R here, gas constant 287 joule per kilogram Kelvin. Gas constant from the table. Okay, 287 joule per kilogram Kelvin. So from pressure R and temperature, you can find density. Okay. From density and volume, mass. And so answer is A, B, C, or D? A, B, C, or D? C. Yep. C. C. 1.11 joule. Actually, it's around 1.116 or 11. It's around 1.116 or 1.117 or something like that. But this one is closest. So the answer is C, 1.11. Okay. The answer is C. Yep, C. Yeah, you correct. You front. So do you have any question? Do you have any question? So this one is will be for the quiz. You only need 1 or 2 equations to find the answer. It's easy. It's similar to this one. Okay, but the quiz I will say about the quiz maybe right before the quiz, because the quiz will be focused on from week 1 to week 4. Okay, now just only week 1. Okay, so fluid mechanics properties. Do you have any question? All right, student, do you have any question? Okay, so if you don't have any question, thank you. Because the tutorial is just only 1 hour and 30 minutes. Okay, not 2 hours as so in the select timetable. 1 hour and 30 minutes, similar to last semester. Okay. So if you have any question, you can email me. My email you can see in UTS Online here. Let me see. To the online student needs to join. No, just only face-to-face student needs to register online now. Okay, because the maximum capacity of this room is 15. I think 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 14 or 13. Only 14 students can attend to face-to-face. So that's why on face-to-face student have to register. Use Google chat box. You can see in the email subject coordinator sent you yesterday. Okay, for online now. My email here. I can show you my email. Okay, my email. Teaching staff, the first one in teaching staff, you can email me you have any question. Okay. Thank you, and see you in the lecture class on Monday. Okay. Thank you. Yeah, see you. And the recording of the online class will be uploaded on UTS Online tomorrow. Okay, I uploaded the recording of lecture class already, and the tutorial, online tutorial tomorrow. Okay, thank you. Do you have a question? Yes. So I might we think maybe we lecture tomorrow on Monday. Yes, during the lecture on Monday. From 1 to 3 p.m. on Monday. And the quiz will be 80 minutes.
Do we have to do it every week?
No, it's only one. On the lab, the solid coordinator will send you your letter. Because the lab is similar to the tutorial, it's drop-in, okay, so you can attend to the lab or not, it depends on you. So, but the capacity, the lab pool is smaller than this one. It's only, I think, it's only 5 or 6 students attend to the lab. Okay, and everyone has to attend it online. Everyone parallel is this one. And the recording will be uploaded on UTS Online. And actually, for the lab on UTS Online, we have everything. You have the recording of last semester. You have the data. You have sample information. Everything is uploaded on UTS Online already. Okay. So, and actually, any question can tell me or recording data. Okay.
It's not the same for
The
students.
data on the UTS Online need use some data, not only one. So maybe it's 1 week and choose one data. Okay, so when you have 10 or more than 10%. Okay. So one group, one data. Okay. Or you can use the data on the lab, on which file, which you will add to the lab. You will add to the online now. You can use the data we have. Or you don't have the data, use the supported data from the online.
So yeah, we don't allocate a region.
Yeah, okay. One. Okay. I will give you more details maybe on 5, 6. Okay. Before the lab, I will give you an announcement before the lab. Okay. Okay. Thank you.